Well, thank you, Sophie, for the introduction, and thank you for having me today. So, I've come here kind of to talk about what basically from the point of view of an academic career, but also, well, in space related research, but also from the perspective of someone who's done a physics degree. So, I'm going to kind of tell you about a bit about me, and then go on to why the degree of doing physics or doing space related degrees is very applicable and makes you a very valuable individual for jobs in not just the space industry, but all over all over industry, outside of space, inside of space. So yeah, as Sophie said, I'm kind of in between jobs. So I've just finished my PhD at University College London, which I'm gonna kind of talk to you from that point of view today, because I start a job in January at the University of California, which I've got on here. But yeah, I haven't started yet, so I can't say much about that. But yeah, so first of all, University College London. This is the Mullard Space Science Laboratory, which is the Space and Climate Physics Department of University College London, in a beautifully located old stately home. And I think it's important to talk about this because it's a kind of a unique place in terms of the UK space research, because we are one of the only university departments that actually not only proposes missions and uses the data from space missions, but also designs, builds, designs and builds and operates space missions as well. So we have been involved in the designing and building of missions that have been instruments that have been to Mars, instruments that are looking at the sun, and many more, which I'll show you it in the next slide. So these are all the rocket launches that we've been in since our opening in the 50s, actually, all the way up until 2017, and I'll show you the more recent ones after this. But MSSL, Mullard Space Science Laboratory, we have had instruments on all of these missions over many years, so including ones that you might have heard of, such as the Cluster mission, Cluster 2 mission, Cassini, that's been to Saturn, almost got it wrong, Mars Express, and ExoMars, which unfortunately isn't going ahead anymore. But you get the point that we, oops, wrong slide. You get the point that we contribute to a whole range of space missions. We build the instruments, and then the data that comes from those, people like me who do the scientific research, we use that data to make scientific discoveries. Some missions that you might have heard of, which are more recent. I'm sure you've all heard of James Webb Space Telescope, which we contributed to in terms of the science that was. So we'll be using the data from James Webb Space Telescope, not me personally, but people at MSSL. Solar Orbiter, this instrument here on the end of this big boom, which is currently in space now. We designed and built that in our clean room, which is attached to the side of the building. Rosalind Franklin rover, which unfortunately is no longer going ahead, as far as I am aware. But we did build the PanCam instrument that goes on top of the ExoMars PanCam rover, as well as the Euclid mission. We've sort of took the lead on that as well. You may or may not have heard of that. And then just one exciting video of when Solar Orbiter launched back in 2020. Oh, never mind, I forgot to update that video, but this was a video of the rocket launching with the Solar Orbiter spacecraft back in February 2020 with the UK built instrument aboard it. So yeah, that was just a bit about where I come from and why, how we kind of contribute to the UK space industry. But a little bit about the science I do now, because I figured that people might be interested in that. So my field, which is the field of space physics or space weather, depending on exactly which part you're doing, focuses on how the sun, which is what we're seeing here, affects the rest of the solar system in terms of the very hot materials that get thrown out of the sun constantly, and the magnetized environment that most solar systems presumably have. So how those plasmas interact with magnetic fields. So you might be aware that the sun constantly throws out all this material known as plasma. And this is a short video of over a few days of the sun's constant outflow of plasma. We call that the solar wind, and it usually flows out of the sun at a constant rate of around 450 kilometers per second, which sounds quite fast, but that's generally quiet time, low level solar activity. But every now and again you get a burst of plasma, such as this one here from 2012. You can kind of see that big ejection of plasma from the sun, which is the things that we've got to sort of become concerned about if we're on Earth and we're protecting our space-based infrastructure. And for those that are interested, plasma is just basically a hot gas made up of charged electrons, protons, charged particles, basically, which is why you kind of see this snowflake effect on the camera, because as those particles pass by, it interferes with the electronics on the spacecraft. And then once that material leaves the sun, those particles, that plasma, propagates out into the solar system in a sort of spiral shape, because the sun is rotating just like the Earth is. And as you can see here, Earth, Venus, Mercury, these are a couple of spacecraft that were launched from Earth. They propagate out and they can interact with those planets. And because this is very hot and very active material that's being thrown out of the sun, if your planet doesn't have a magnetic field, you've got to worry about that. So fortunately, the Earth does have a magnetic field. I'm sure you've seen a diagram similar to this at some point, where you have a simple bar magnet which creates a dipole magnetic field, meaning that there's a north pole and a south pole, and the magnetic field flows from north to south. And because the Earth is magnetized and the plasma leaving the sun is electrically charged, that means it interacts with our magnetic field, and it kind of acts like a shield from the sun's plasma. So it deflects plasma around the Earth and kind of stretches our field. It sort of compresses it at the front, just like that, compresses our magnetic field at the day side close to the sun and stretches it out at the night side. There we go. I'll just let this play through. And the reason we've got to be concerned about that is because the reason we still have to be concerned is because some of those plasma particles do find their way into the Earth's magnetosphere, and they are damaging to our space-based infrastructure, as I've said. And a particularly hot part of Earth's the sort of space surrounding Earth is a result of the magnetic field trapping these solar particles. And it's a region called the Van Allen radiation belt, which is my sort of specific area of research. And the reason we need to worry about those is because they engulf such a large region of space close to Earth. I suppose more significantly, regions like geostationary orbit, which is the region where satellites orbit the Earth at the same rate at which Earth spins. So we've got a lot of satellites there giving us things such as communications, GPS, TV, weather satellite, all that kind of thing, operate in this radiation belt region, or at least pass through it. And this is a sort of example of all of the, I think this includes debris as well, but it kind of illustrates just the sort of mass of satellites that surround Earth that are vulnerable to space radiation, as we name these particles when they get trapped in the Earth's magnetosphere. And this is an example of the sort of damage they can do to satellites. So if you think about all the ways we use satellites, so as I've mentioned, like communications, weather, telephone signal, TV signal, all these things we rely on more and more as we go into the future. It's important to understand space weather to be able to protect those pieces of infrastructure. And the more sort of natural phenomena that occurs from space weather is things like this. So the aurora, or the northern lights, you may have heard of the Aurora Borealis, and the southern lights, the Aurora Australis. When those hot solar particles hit the Earth's atmosphere, some of them do, not many of them, but the ones that do, we get this sort of neon light effect on the atmosphere, which we see as the aurora, which you can see from certain parts of the world, such as northern Canada, well, a lot of Canada actually, and sort of Scandinavia, Iceland. Some of you might have been to Svalbard as well. Great places to see the aurora. And then this going closer to Earth, all this activity going on in space as a result of our magnetic field and the sun's hot solar particles creates disturbances in our sort of space, in our magnetic field in space, which can affect our atmosphere as well. So the movement of the magnetic field can drive electric currents through our atmosphere, called ionospheric currents. And when we've got electric currents flowing through our atmosphere, that's a problem for things like power lines, which we definitely need to protect because we rely on those things. When you get a strong electric current as a result of strong solar activity, you can overload them power lines, and you can basically trip a power grid, and you can have power cuts, and power grids can be completely destroyed in the worst case scenario. And then you've got to think about things like communication. These electric currents can disturb communications and GPS, for example, which we rely on even more and more every day. So that was kind of a crash course of my field and what I do, which is called space weather. And since this is a careers conference, I'm going to move on now to sort of how I got there, and then how at each point along that line I could have gone somewhere else because of the skills that I'd picked up, and which you will presumably pick up if you go towards any kind of space-based career. So I always like to point out that I was born in Doncaster, because you don't have to be from anywhere special to go into the space industry. A lot of people I know are sort of born in London or grew up in London and grew up in very lucky, some people that grew up in Leicester, very close to the space centre, but which is nothing wrong with that, of course. I do love Leicester, I live there myself, but it doesn't matter where you're from, you can always find your way into the space industry. You don't have to be sort of close to anywhere in particular. Because I was able to then go and study at the University of Leicester. I did a degree in physics with astrophysics, did a 4-year master's degree, and then did a PhD at Mullard Space Science Laboratory, as I've just explained, in radiation belt physics. And then I'll be moving on, starting in January, to do a postdoctoral position doing similar research at the University of California in Berkeley. So as a sort of research scientist, I kind of want to explain what that's about. It's an extremely varied career path. Although most of my time is spent in an office on a computer, I'm doing a whole host of different things. So that using the measurements from the spacecraft that we send up, or whoever sends up into space, we use computer code, computer programming to analyze data. Once we've got our findings from that data, we then write reports and papers about the findings, and then we go to conferences and meetings to tell everyone else about the research that we've done. So there's a whole range of skills going on there, a whole range of experiences. A few photos of me traveling about here. Here's me at a conference presenting my work that I did in New Orleans, which is what this picture is. I got to spend 3 months in Canada working with another research group. That's where I saw the aurora there. This is from my bedroom window, amazingly. So it's a whole sort of variation of experiences, and specifically a whole variation of skills. So if I was in person at this point, I'd get people to shout out skills, but I'll have to just tell you for now. So as a physicist, in doing a physics degree, the obvious ones, such as learning how to do mathematics, learning problem solving skills, computer programming, because you need to, such complex problems require high processing power to be able to solve them. And a lot of that is spent on my own in my office, or working in groups as well, to solve these kinds of problems. So you're already picking up loads of skills. Go to conferences, speak to people, and write about the research. So there's lots of communication skills going on. And of course, you've got to balance all these things. So you've got to be organized, you've got to be creative, and you've got to come up with new ideas. So there's a whole host of skills there from doing research, but as well as doing a physics degree at undergraduate level or master's level. So kind of moving on to the point that physics opens far more doors than it closes, if it closes any at all. So we've already heard from two speakers today talking about the range of opportunities in space careers, and I do want to highlight careers outside of space as well, because you know, whether you're sort of thinking about doing a physics degree, not sure, don't know whether you want to do this or that, well, I'll tell you that physics offers so much more than just doing physics. So this is sort of generic pictures I found on the internet, but this is supposed to be engineering. So anyone thinking physics or engineering, I know loads of physicists that then got it straight from their degree, got a job as an engineer. So it's versatile in that way as well. Teaching, your knowledge base as someone who's done a degree in physics is very, very valuable, particularly to teach other students as well, from all ages. This is supposed to be representing sort of data analysts, so whether you're interested in going into finance or going into data science, and data science can apply to so many different things, any kind of business, government, anything you like. I'm sure you've all seen plenty of graphs over the last few years with the COVID pandemic. Data science, well, maybe sometimes you can question this, but data scientists will have been involved in that whole process of working out what to do, how the government should react, for example, to a COVID outbreak. Astronauts. So this this astronaut is Sally Ride. She was the first female US astronaut. She's got a physics degree, and the skills that she's using as an astronaut, things like the communication, the organization, they have to juggle so many different skills and use so many different skills that undoubtedly would have been picked up along the way doing a physics degree. People who are interested in video games, well, physicists have a huge place in the video game industry. Computer programs need to be written, physics engines, anyone that plays any sort of open world game, even a simple game like Mario, someone has to calculate how high he jumps and what his trajectory is. There's all sorts of applications for your mathematics, for your problem solving, communication. Some of you may recognize who this is. This is Angela Merkel. She was the former Chancellor of Germany, or the sort of equivalent to our Prime Minister. She did a degree in physics. And she also did a PhD in quantum chemistry. And if you think about it, physics degree is extremely applicable in a politician's case, because they have to organize, juggle loads of things. They have to work in teams. They have to work on their own. They have to be able to communicate and articulate their ideas and their findings very clearly. So a physics degree has got so many different skills. And then one final one, some of you might recognize that's Brentford Football Club. The reason I point that out is because Brentford Football Club were a sort of pioneer in data science in football. So their owner made a lot of money in business. He had a physics degree. He bought Brentford because they were his hometown club. And then he employed loads of data scientists to analyze the data of football players, to sort of give them an advantage in the market to buy the best players and so on, for a cheaper price where they might have been overlooked by a bigger club. And anyone that follows football will know that they are in the top league in the UK now. So they're in the English Premier League. So lots of wide-ranging uses for physics, which is kind of brings me to my final overarching point, is that everywhere in your life there is physics. So you doing a undergraduate physics degree or something similar, you will have learnt skills that are needed in every walk of life, as we talked about, all the way from working as a data scientist, as an astronaut, to a politician, and so on. So and all the engineering jobs that we've already heard about today. It opens doors, not closes them. So as I said, if anyone is unsure, don't worry about doing a physics degree over something else, because you're certainly not going to close any doors. You're always going to gain from physics. You're always going to open new doors. And you don't. And I also like to mention, like, you don't need to be super smart. Like I don't even believe that kind of exists. I think it just depends on how you apply yourself. I think if you enjoy what you do, if you sort of follow what you're interested in, then it really doesn't matter. You're going to gain those skills, and you're gonna be able to apply them. So that's the end of my talk. I forgot to set my timer, so I have no idea where I am, but I'm happy to answer any kind of questions either now or in the panel about sort of what I do, or physics careers in general, and what I've spoken about. So thank you very much.